Resuming recording.
Perfect.
All right, you should see that. So now you are being recorded for future VNarCon, and will it go on YouTube in a few months, maybe?
Yes,
Yeah.
it will. Yep.
Okay, so you will be stars on YouTube.
Joyce, quick question. Do we usually, when I was screen sharing previous in the practice session, I had a little up caret by my screen share icon. I don't have that yet today.
Okay, but you aren't sharing your screen right now, right?
Well, correct, but even before right to the right of the green screen share icon, there would be like this little up caret.
Yep, you will be able to do that. You'll be able to do that once Joyce calls on you. She's going to make you a co-host, and when she makes you a co-host, that will allow you to screen share.
Okay, can we just do a quick microphone check? Can you hear me okay?
Yes, I can hear Tom. I can hear Steve. Ethan, do you want to unmute? It looks like you're all able to unmute. Yeah. It looks like you're all able to unmute yourselves, which is interesting. Sean, can you unmute yourself? Yeah. So
it would seem so.
Yeah, so I think that I don't want anyone talking over the presenters during the presentations, so please keep yourself muted, and if I hear background, I may have to jump in and mute somebody unless we have, and Todd, maybe you can do the same if you hear people talking over the background, because I don't see a way to disable.
Joyce, I'd gladly do that. Can you make me a co-host now?
Absolutely. Okay. And I'm also right now going to make Ethan a co-host, since Ethan, you are the first speaker. You can have multiple co-hosts, I believe.
Yes, you can.
Okay, all right. And Sean, I was going to make you a co-host. So let me see if I can find you. So if anything goes wrong, you can jump in. And also, so you can ask questions. And then I'm waiting for Ryan. And I will make him a co-host. Otherwise, and Bernard needs to get on here eventually when he's second, he comes second. And Tom is third and Steve is fourth. We're up to 19.
Yeah, it'll populate heavily after the top of the end.
Yes.
Yeah.
I'll make a few announcements. Go ahead. Sorry, Todd.
Yeah, I want to just point out, we had to use this last night during Manufax to find people. The participants list has a little search bar. Once this grows big, that search bar was really helpful for us to be able to, when you wanted to find a speaker, that's what we were using.
Thank you. See Ryan yet? And for the speakers that are here, I am planning to give you a 3-minute warning while you're speaking. I will just say 3 minutes or hold my fingers up or something. And that means you have 3 minutes left. And if you are still talking more than like 20 seconds past your 20 minutes, I'll probably mute you because we need to stay to time. I don't want to run this over and be unfair to any one contestant. On the other hand, if you are shorter than 20 minutes and we don't have too many questions, I may go on to the next speaker and start them early. So just so we haven't advertised a set start time for each of you, so we don't need to hold to a start time. Okay, let me see, is Ryan here yet? Yes, he is. Ryan is here.
My name is Christian. Okay. I've been into rocketry since the...
Oops, somebody was talking.
That was my mistake. I had a live mic. I'll turn it off.
Oh, all right. I'm, Ryan, you don't have your last name on your identification. So
I don't know,
I'm
how do I
hoping,
fix that?
I'm not sure, but I'm going to unmute you
Oh,
as
I see
long
how
as
to
you
fix
are
it.
Ryan, the judge, and not Ryan, a random participant that's gotten onto the Zoom.
I just figured out how to fix it.
Okay. Yeah, I
That's
see you now.
weird. I
Okay.
never noticed it doesn't have my name before.
All right. I'm making you a co-host now, so I know you're the correct Ryan. Okay. All right. So it's 3 o'clock, and I think people will filter in a little bit, but let's get started. Welcome to the first ever virtual NARCON R&D presentations. We're going to try to run this as much as possible, like we used to do in at a NARUM for 2 or 3 evenings. We had 4 excellent entries this year, and I thought the quality was really high because you were all doing it because you love R&D, not because you're trying to get flight points for the national championship, I think. But they're all excellent, so it's going to be a hard decision. So the way we'll run this is each speaker gets 20 minutes. We have about 5 to 10 minutes after that for questions and to switch speakers. So we'll have the judges ask questions first, and you, the 3 judges, can unmute yourselves and ask the questions directly. And then I will look at the chat where you can post questions if you are in the audience, and I will read the question to the participant. And then when we get close to our half hour or time to switch, we will bring up the next speaker. And so I'm going to ask our first speaker, Ethan Goldberg, who's our B Division contestant, to share his screen. And if you'd like to put it on full screen, that would be
And
great.
can you see my screen right now?
Yes.
Okay, perfect. All right, so for R&D, I did finding the relationship between reefing length and descent rate. So here's a picture of the model that I used for my testing here on the pad. So there were 2 objectives. The main objective was to find the relationship between the reefing length and descent rate. And so for that, it was kind of, is it linear? Is it exponential? Like what is this relationship? And then while I was working on it, I thought, well, if I can find the relationship, maybe I could make an equation that you put in, what your descent time is without reefing, and then say I want, I have a 40-second descent time, I want to be at 35 seconds. How much more should I reef it to get to what I want to be at? So that was kind of a secondary objective that I had kind of thought of later. And then here I have a picture of a TARC rocket, or arc rocket, and I'll talk about that more as one of the things that I thought, this research could benefit. So my hypothesis was that the relationship would be an exponential relationship. I came to this hypothesis mostly because of, as the line length is decreased by reefing, the area is decreased exponentially. So that's pretty much how I came up with that idea. So for the design of the rocket, I just built a simple rocket, which is in the photo here, with an ejection baffle. The rocket weighed about 78 grams. I used a 12-inch flat hexagonal parachute, which I was shown on the last slide. That had 6 lines. The lines were also 12 inches long. Additionally, the rocket picture here was the second version. The original one had a 3D printed nose cone. So for procedure, I picked I picked 5 lengths for reefing the chute. So I think that's in a table on the next slide. And so for each of those line lengths, I made a mark, and then I put blue tape to reef it at that mark. And this is one after it was reefed to the last space. So it's all the way reefed. And then again, the line length was 12 inches unreefed. This doesn't have that on the next slide. So the reef lengths were no reef for control, 2-inch reefing, 4-inch, 6-inch, and 8-inch, measured from the bottom of the lines. And then after that, I timed each launch so from first motion to landing. And each flight was flown with a C65 motor. So here's the equipment and facilities used. So this is the park that I used. It's in Walkersville, Maryland. And then I used just SD's pad with a 3/16 launch rod. So here is the raw data. So the flight number, reef length, and flight time, which is in seconds. And then the notes. So a lot of my flights had a little bit of a wobble off the pad, which I'll talk more about in the section about errors. But I think this may have caused some errors during the flights. So analyzing the data, what I did is I changed the reefing length into percentage reefed, just to make it so the data would apply more to different size chutes. You know, if it was a chute that was 24 inches instead of 12 inches, with percentage, you could, transfer the data more easily. So the percentage, I just divided the amount that it was reefed by the 12 inches. And then the next thing that I did was I changed the flight time into percent change in descent rate, which took a little bit of manipulation. So for that, what I did is I took the average descent time for each reefing length. So each one I did 2 trials of each reefing length, and I would find the average of those two. And then I subtracted from that 6.7 seconds. So 6.7 was the time from launch to apogee, as predicted by simulation. So I wanted to do that just to subtract that, because that would be the same for every flight. And then I did 600 divided by that new flight time to find the descent rate in feet per second. And then I took that number and I subtracted the initial descent rate of the control. And then I divided by the initial descent rate to basically find the percent change in descent rate from the initial control flights. So I then took all of those and I plotted them in a graph, and I got this exponential curve, which is shown here. So the parameters are here too. And so basically what this shows is that as it's reefed more, the descent rate is exponentially faster. So by the time you get to the last reefing, which is 8 inches, which would be 2/3 or 66%, the descent rate was half or double in feet per second of the original descent rate without having it reefed at all. And so over on the left side, I have the equation for the drag of a parachute. And so what I figure out from this data is my new hypothesis of kind of involving what data I have is that as it's being reefed more, the diameter of the chute is decreased linearly. But as the diameter is decreased linearly, the area of the chute that's exposed, which is a circle, becomes exponentially smaller because the area of a circle is pi r squared. And so this drag formula includes the area of the circle. And then another thing that I also think is that the area alone is not the only thing changing from reefing the parachute. So I believe that the drag coefficient is also being increased because the parachute is turning in from more of a flat sheet into more of a hemispherical shape. And the hemispherical shape is known to have a higher coefficient of drag, which is also in the drag of the parachute equation. And then the next slide. So examples of applications. So the data that I got can be used for a lot of applications, but the biggest one that I can think of is any competition that involves precision duration. So the big one would be American Rocketry Challenge, but also NAR, like Precision Fragile Payload, FAI, S2P, or there's probably others that I'm not thinking of. And so for these competitions, targeting a specific descent time is one thing that you want to do for points. And so with that, many teams or individuals will reef their parachute to try and get it to hit the exact descent time that they want. And then just looking specifically at ARC, because that's the biggest one of these competitions, many teams already use equations to determine how much weight to add to their model to hit the target altitude. This is kind of when I had thought about, could I make an equation that explains, how much more to reef to decrease the descent time or increase the descent time to what is desired. And so some teams are already using those kind of equations for altitude. So we would say, right now the rocket weighs 330 grams. We want it to go, 10 feet lower. How much more weight should we add? So I thought something similar could be made for the parachutes. And then so errors. There were a lot of errors in the data. And so I have a picture of one of them here. The shock cord got tangled around the motor clip. So that was kind of unfortunate. But there are some issues with the original design. So in this picture is the original design that has a 3D printed nose cone. So 3D printed nose cone broke on some of the flights, and it caused the nose cone to separate. And obviously that means the rocket was lighter on descent. Another big issue was the launch rod. It was a little bit windy on the day, and so as it launched, it kind of whipped a little bit coming off the pad. And so some of the flights had straighter and higher launches than others. And then another issue was that it was timed by hand with a timer on the ground. And so because of this, it could have been off a little bit from flight to flight. Here's my budget. Not really much on that slide. So past work. So I looked through all of the old R&D reports to find something kind of similar that I thought was interesting. So I found this R&D from this Parachute Performance, Jim Reed, 1974. So I thought it was interesting. So in this report, Jim Reed was comparing the shroud line length to the coefficient of drag. And he was using one of the same equations that I was using for the drag of the parachute. But what he was doing was not reefing the chute. He had multiple chutes made with shorter or longer shroud line lengths. And so this is the graph that he got. So it's the shroud line length getting longer towards the top, and the shroud line length on the bottom. Yeah. And then, so then I took his graph and I noticed it had a kind of similar shape to mine. So when I inverted it, it actually gave a very similar exponential curve to the graph that I had. So I thought that was really interesting. And this is also because his graph was like, as it gets longer, then the descent rate would increase. And mine was, as it gets shorter, it would decrease. So that explains why the graph would be inverted the way it was. And then future work. So I had a few ideas of how I could improve this for any, future project. So the biggest thing that I thought about was using an altimeter. Many of them, I know, like Peanuts, which is what I have a picture of, and many other altimeters give an actual descent rate, usually in feet per second or meters per second. So using an altimeter, you could get the actual descent rate, and this would allow a lot of the air to be taken out, so you wouldn't have to kind of rely on each flight going to the same altitude, because if one flight went to a lower altitude, the descent rate wouldn't be affected by your timing and assuming it went to a certain altitude. It would also help with some flights might have some variation. And then another thing that I thought about was in the future using other parachute sizes or shapes. So, to see if how the results translate to other parachute sizes. And then I have a picture of an X chute. So X chutes are commonly used by some ARC teams. I don't know how many use them, but I know some use them because they believe that they are more consistent than round chutes or hemispherical chutes. And so I know, since ARC is one of the main things that I'm looking at, I thought that might be interesting to try and do the reefing with that, as the drag is a little bit different on that chute. Yeah, that is the end of my slideshow. So I'll open up to questions.
Okay, thank you. You finished with about 5 minutes, 4.5 minutes left. Great. So I'm going to ask Ryan to ask a first set of questions. So Ryan, go ahead.
Awesome. Yes, thank you. Thank you very much, Ethan. That was an awesome project and an awesome report. Really enjoyed reading it, and really enjoyed the presentation. The first question I had for you is when you looked at the prior work that was done by the prior report that was kind of trying to actually apparently increase duration or increase drag, did you have any thoughts about going with a parachute, starting out with a parachute with longer lines? Because if I understand it correct, your parachute was 12 inches in diameter, and the shot lines were also 12 inches.
Yeah, so the parachute that I used was purchased, so I didn't really have that much control over the line length. I could have made my own, but I kind of thought about that after I had already done a lot of the data, because I kind of went straight into like, let me collect all the data before I write the report. And then after that, I'm like, oh, maybe it would have been interesting to try and see what would happen if the lines were 16 inches long or something like that. So yeah, I didn't really think about that until after I did the data.
Okay. And then also in your data, I noticed that you recorded things like if the launch went straight or straight. Did any of the flights not eject immediately?
So most of the flights ejected. So the straight flights all ejected pretty much at the same point.
Okay.
Some of the flights that were angled a little bit more were definitely ejected slightly later.
Okay.
I'm thinking that the apogee, so Open Rocket predicted the 600 feet apogee that I was using for the calculations. I think some of them that weren't as straight may have only gone like 500 feet. So those ones seem to have, some of them have a lower ejection altitude.
What about chute deployment?
So the chute deployment was pretty consistent from what I remember across all of the flights. Yeah.
Okay. All right. I'll go ahead and pass it over to Sean then for some questions, if that's okay with you, Joyce.
That's what I would do. Sean, you might have to unmute if you're muted.
I did, yes.
Okay.
So remind me, you said you had some thoughts on how to remove some variability from your test data. Um, what what do you think would improve the variability in the data itself the most to your eye?
I think the thing that would really help the most would be using an altimeter to measure the descent rate. So I think because I have experience using many different altimeters, but they're pretty reliable in descent rate, and I think that would take out a lot of the like when did it eject, how high did it go, out of creating a lot of variability, because I think that's really where the variability is created the most. I think also I could do more trials, but I think the biggest thing would just be trying to get something to actually measure the descent rate. And an altimeter is not the only thing that could do that. And there are other options, but I think altimeter would be the easiest.
Cool. And you mentioned in your slide where you said, you thought it could be that both the area and the coefficient of drag were changing. How would you quantify those two things together to kind of unify them, or how would you separate them out to get an idea of one, both, or the either uh, in quantifying how these things affected your descent rate?
That's a tricky one. So I think the biggest thing for that would be trying to see like maybe you could make different shoots with different areas and also hemispherical shape to them to try and see like how much is a more hemispherical shape increasing the drag, and try and separate those out by making shoots that specifically have one or the other thing changed about them.
Gotcha. Let's see. Joyce, if you pass it on to our next judge for more questions.
Okay, that's me. I am the next judge. It's just the three of us.
Yep.
Yeah. So anyway, I have two questions. One of them is you mentioned the rod whip. And what could you do to get rid of rod whip?
So yeah, there's a lot of things. So I guess the first thing is a better launch pad. That's a bit, more sturdy. Also just something other than a rod, like a rail. It's kind of a smallish rocket, so the rail buttons are kind of large on it. But I know there's like micro rail buttons. Also, I have a tower launcher, so I could have used that. It's a lot more stable than the rod.
Okay, very good. And then I have more of a math question. Your hypothesis was an exponential, but that graph you showed was fitting your data, your 5 data points, to a polynomial. So, can you talk about the difference maybe between what you mean by exponential and what you mean by a polynomial? And what is a polynomial? Because you had, something equals ax squared plus bx plus c. And that's a polynomial.
Yeah, so the polynomial was what the program that I was using to graph had in it. So I guess there might be some difference in the shape, but I'm not exactly sure because I don't know exactly. I'm not that much of a math person. So I kind of just what I graphed it in, I just use like, oh, has the line of best fit for this. I'm not exactly sure for that one.
Okay. Yeah, you might try fitting it with some other, you probably need more points too, but you could probably try fitting it with some other kinds of functions. And there might be programs that could help you with that, or something you'll learn more in math as you go along. Okay. Yeah. All right. I think we have a little time for the audience. So if you have questions, please put them in the chat and I will ask them. I could go back around another round of the judges, but I think I think we're running close to the end of our time, so. Okay, well, one person asked, what grade are you in, Ethan?
So I'm a junior.
Okay, high school junior, okay. How many times have you been in the TARC program?
So this is my 3rd year doing TARC.
Okay, and you intend to do TARC next year?
Yes.
Okay. Bill Cook asks, did you do all the flights on the same day?
Yeah, all the flights were on the same day using that data. I did a few flights before to, test the rocket, but those flights were not included in the data.
Okay. Any more questions from the audience in the chat?
Yeah, there's also some posts in the meeting. Oh, okay. I'm sorry. Never mind. Those showed up late for me. I was saying there's some posts in the meeting chat, but some of them the earlier ones were more kind of statements rather than questions.
Okay, yeah, there were, Ethan, I would encourage you to look at the chat after your talk because there are two. One of them is Bob Kaplow put in a link to another reference he thought you should look at that would be relevant. I haven't opened it. I don't know what it is yet. And then David Carter has an interesting comment. You've invalidated any parachute descent rate calculator that doesn't factor in shroud length. So that tells you that some of these calculators may have limitations if you ever use them, standalone. Think about shroud length as well because
Yeah,
of your research.
Yeah, shroud length is definitely a major thing in descent rate. So I know a lot of people say the 1.5 times the length, 1.5 times the diameter shroud length is the optimal for competition shoots. So I think a lot of calculators would probably use that.
Yep, that makes sense. But I guess it's important to know what your assumptions are when you use some software written by somebody else. What did they build in for assumptions? Yeah. Okay, well, thank you so much for your presentation. I think we're going to move on, and I'm going to I'm going to make Bernard Colley the co-host now.
Okay, thank you.
So, thank you, Ethan. And then Bernard, you can share your slides.
Okay, just unmuted. Hopefully that worked.
Right, your slides are not here yet.
Share desktop 1. Oh, I got to push the button down here that says share. That will do it.
Okay, and then can you put it in full screen?
And
All right.
get the windows off. Actually, I can take this all the way up. Here we go. That's probably even a little bit better.
That looks pretty good. Okay. All right, and
Okay.
I'll give you a 3-minute warning, so you can start when ready.
Okay, well, I'll be happy to have all the extra time Ryan was able to get for me.
You probably get it.
Because I talk too much. Anyway, so the subject is 9-volt batteries in use in rockets with an emphasis on launch controllers, but also for deployment computers. So why am I doing this project? How I got into it, some of the analysis and results, and then for the 4 battery types that were tested, we'll go through a little more detail of each of how they behave. And then I'll have some recommendations at the end. A couple of mentions of what other rabbit holes one could go down. So the reason I decided to do this project, it started with a thread on the Rocketry Forum a year ago by a gentleman named Martin Quancy, who I know is, or Quanchi, who is listening in, I know. And one of the things he showed by buying some batteries, doing some interesting manual tests, and then taking them apart was that our go-to brands are not what they used to be. And since before I got back into rockets, I was an electric airplane guy, and I did a lot of time testing power systems and such. I said, oh, I could probably do some more of this. And then this last year, Aerotech brought out a new 9-volt controller, the little phaser that Gary mentioned last night in his manufacturer's forum. And its documentation says, use lithium batteries. And then I just more recently discovered that, well, okay, so the only lithium battery I can go buy is the Energizer Ultimate, and that sucker costs over $15 now, which is over half the cost of a phaser. So I thought I would see if we could find some alternatives that weren't so expensive, and also kind of go back over what Martin had done, and then extend that methodology to lithium batteries. Lithium 9-volt batteries. And back in the title, it said primary batteries. So I didn't hit that. Primary batteries are non-rechargeables, use once and throw away. I did not go down and look at anything rechargeable. So what things to test? And this background image is the 4 9-volt controllers that I have laying around that could all use these results directly. So Martin found that there are 2 different ways alkaline batteries are made right now. And so, of course, I had to test samples of each. And in fact, he sent me some of his samples to do that with. And then, as I mentioned, the phaser came out last year, late last year, and it calls for using lithium batteries. So I figured, well, I'm going to have to look at those too. So what did I do? Well, I wanted to be able to do both live fires and some kind of simulation, just because otherwise I'd be burning hundreds of igniters before this was done. And I wanted to be able to log current and voltage and such while the testing was being made. And so in casting around to some of my older equipment, I came across the Hyperion E-meter 2, which is a tool that was created in Australia and made in Taiwan for testing electric power systems. And it's a data logger. This little bit in the middle can sample current and voltage. It calculates, it stores the data. It can sample up to 8 hertz, which isn't great for this kind of thing, but it was the best I had to hand. And then it saves the data as it logs it onto an SD card, which you can pull out and stick in a computer. And that file is just essentially a comma separated values file. So it's easy to suck it into a spreadsheet or a plotting program and manipulate it. So this is the setup on the left hand of the slide there, with the E-meter data unit connected between the battery that's the subject of the test and the phaser, which is the launch controller in this particular case, that will ultimately fire this Estes igniter when I do a live igniter test. And for the most part, I use the straw-colored Estes solar igniters that everybody loves to hate, because I had a bunch of those that I hadn't yet prepared to use. Had a bunch. I fired a couple of other things too, just to cross-validate. And so the actual process went like this: hook it up, let the thing settle for a minute, because the E-meter drew power from the test battery to drive the sampling unit. So it had to let that settle. Put the key in the controller, count down from 10, push the button for 5 seconds or so. This made it consistent whether the igniter fired all the way and burned out or not. Watch what happened, write something down, stop the log recording, go over to the peak screen, which is another screen on here, and I just took a picture of it with my phone so I could record the value there of how far the voltage sagged, how much current, what the wattage was of that particular firing. And the E-meter also has an internal battery resistance estimation tool, which I wrote down the values from, but I haven't really done anything with that data, although I'll come back to that. And if the igniter firing went off well, then I went and switched it over to the program setup and ran that. So for the automated testing, what I did was, instead of the phaser on the output of the data unit, I hooked up a HS55 servo and a micro switch in the place of the launch controller. And then I had these leads from an old Estes electron beam. And in the clips was a power resistor. And I think I'm kind of anticipating my slides here, so let's just go on. Yeah. Battery is the same. Servo-operated switch on the output connected to electron beam leads. And then to simulate an igniter, I got some power resistors off of Amazon, and I wired a pair of them in parallel to simulate an Estes igniter. Estes gives you the specifics of the igniter characteristics on every sheet that comes in every pack of motors. And I got really close. I got 0.67 ohm effective resistance for 0.69 simulation. I wish Aerotech had data like this, but when I asked, they basically said, we don't know, and they vary a lot. So the automated test went like this: connect it up, let things settle, go to the run profile screen and start the igniter test program. This little thing that's black up here in the corner is the actual program. It's just a servo position and a time. A servo position and a time. And this third line is servo hard over 2¼ seconds. So that was the on time. And this loop took about 5 minutes to run. And I just set the thing to run it for run it repeat. And then I set a timer for 2 hours and walked off and let it go. And then after it was done, stopped it and took the card out of the e-meter while I was waiting to do the next live firing and save the data on the computer. So if you can imagine logging a 2-hour run at 8 hertz, that's a big file. The files typically were 57,500 lines long. But my lovely new MacBook Pro was able to handle files that size without any problem. So then I put them into Magicplot and plotted out the results of current and voltage for each of these tests. Oh, I think I missed it when I was going back here. I went back after every automated test and did another live firing. And then if the live firing was good, in other words, the igniter lit up nice and bright, I went and did another program test, and then back and forth until the igniter, the test igniter didn't look like it would have launched anything. Anyway, so I plotted the different runs for each battery together, and I also did some comparisons, and I also put the peak screen values into a spreadsheet, which was not in my report, but is attached to the version I sent to Joyce last night. So here's what some of the plots look like. You can't see them probably, it's because they're too small, but we'll get into specifics here in a bit. This first one is 2 different live igniter firings on a really crappy battery. And this next one to the right of it is the one automated run for that same crappy battery. This one in the lower left is a comparison of the currents for one run of the simulated for 4 different battery types. And I'll show you that one in more detail in a little while. And this one in the lower right, this is the current and voltage for live igniter firings for one particular kind of battery, which was really interesting. And we'll get to that in a bit. So these are the 4 physical types of batteries that were tested. And you can see both in front of the teardown ones, the ones behind them are another example of the same battery. So there are alkalines that have 4 cylindrical quad A size cells in them. There are alkaline batteries that have these pressed together flat rectangular things, and you notice the Duracell is one of those. And then there's the lithium packs or lithium batteries, the Energizer Ultimate, and this Vonico, which I got off of Amazon, which is when you take the labels off, you can't tell the difference looking at them inside. And then these ones that I never even knew existed until I got into this, which are primary lithium pouch cells batteries. So as we go, bear in mind that it takes 12 watts or so to burn out an Estes starter, 12 watts into it or a little more. So the first thing was I immediately saw the same thing that Martin had seen. The 6 quad A cell batteries will fire an igniter and will fire a number of times. And so, whoops. Oh yeah. Yeah. The quad A cells are usable. The ones with the rectangular cells aren't. They're terrible. And when Chris showed a Duracell in his pitch last night in the manufacturer's forum, I was almost screamed at him through the TV about that. Anyway, come back to that. The lithium ones are way better, but then they cost way more. And the pouch cells, as I say, have an interesting twist. We'll get into that in more detail in a minute. So now, battery by battery. So 6LR61, you'll find that on the outside of most any of these batteries that have the 4 quad A cells inside. And you want to look for that. And this is the way they all were until not too long ago. And kind of what kicked off Ms. Martin's tests was finding that Duracells weren't that way anymore. These easily fire an ESTA solar starter when they're new. And then after they've been through one simulated 2-hour run, which turned out to be 19 firings, as it turned out, they'll still probably light a motor. The starter doesn't burn out, but it'll still probably light a motor. After you've run another 19 simulated firings, they're toast. The igniter will hardly glow. So if you put one of these into a launch controller, I expect you probably get 20 flights off of it, give or take, maybe a little more before you had to buy a new one. But unfortunately, all the name brands that we can just go buy in the store are made with this horrible, or not made this way anymore. I'm getting ahead of myself. They don't make them that way anymore. They make them with the rectangular cells. So instead, you've got to go buy them online, or I think Walmart carries the Rayovac Fusions. But everywhere otherwise, it's Amazon or eBay. But you want to look for 6LR61 on the outside. So here are 4 live firings off of that PK Cell Ultra. This is one of the ones that Martin sent me. This first one is the fresh battery firing, and you can see it burned out in about 2 seconds, because that's all the longer the pulse is. Holding the button down past that point doesn't do any good. The next one, this is the first one after one automated run. We're still getting about 2 amps into the igniter when you first push the button, and then it sags. This one did not burn out, but it probably would have launched a model. This third one is after the second 19 runs, and now we're less than 2 amps going into the igniter, and that's not going to do anything. This last one was just right after that. Instead of another automated run, this was a StarTech. I just wanted to see if it would burn. It did, but not with not much enthusiasm. And these are the 2 automated runs. You can see the voltage falls off fairly quickly on the first time through, but the current and you notice the currents into this resistor is a little bit more than it was into the igniter. A little over 3 amps at the beginning, sagging to about 2.5 at the end. The second run started at about 2.5, and it was down to about 2 at the end. So this is fairly typical of the 4 quad A cell type alkaline batteries. This is an Amazon Basics one, but since this is kind of redundant, and again, this one fired the igniter, burned it out almost instantly, and then the other 2 were less enthusiastic. The second one probably would have launched a rocket. This third one, no, sorry. Okay. The other alkaline type are these pressed cells. And they say either 6LF22 or 6LP3146 on them. And you see these are all these flat stacked. This is the Rayovac, the common Rayovac. This is the Duracell. This up here at the top is an Energizer that I opted not to buy, just to test at Target, because it said 6LF22 on it, so I already kind of knew what it was going to be like. These don't even can barely warm up a starter even the first time you try them. Brand new out of the package. And yeah, after one 19 cycle run, forget it. It's really, yes. Basically, don't use these. Don't buy these if you're going to put them in a rocket, or use them to launch rockets, because they're not going to launch a rocket. And here is the Duracell, the initial firing, 1 3/4 amps into it off the fresh battery, and then after the automated run, it even less. Yeah, just don't. See, it started off even just barely over 2 amps into the resistors on the automated testing. So now we get to the good stuff. The lithiums, externally, they're either in a nice sharp edged case, like this Vonico, or the Energizer, or they're not. There's no label on the outside that tells you how they're built like the alkalines are. And these will run at least 4 times as long as the best of the alkalines.
You have 3 minutes. 3
Oh my
minutes.
goodness. Okay. All right. So let's get to the pouch cells then. These live up to what the phaser calls for. And firings, nice flat voltage. There's 6 of them across here, all laid on top of one another. You can't hardly tell the difference. Vonico, not quite as good as Energizer. Pouch cells are interesting. I didn't know these existed. And when I first pushed the button, the thing went right, the igniter would glow, but it didn't burn out. And I didn't know what was going on. It turns out there's a current limiter inside that prevents you from, so you get a good spike, and then if you don't wait long enough, you don't get anything. I went ahead and started testing them, and when I took one apart, I found out what's going on. There are these lithium manganese dioxide pouch cells inside. Fortunately, Amazon left the label on the cells. And then there's this little current limiter, which is made in Shanghai. And this, so that self-resetting fuse lets enough power out that you can actually fire a starter, even though it doesn't burn it out. It's plenty bright enough. And then these things just go and go and go because of that limiter prevents you from pulling too much out. And I've been flying a half-used one in this phaser that I was showing a moment ago. I've gotten 33 flights off of it since then with nothing that I could blame on the battery for misfires. So in launch controllers, these are the way to go. I would strongly recommend for a deployment case where you need to, you have to allow the time for the fuse to reset, test your setup. This is, I promised I'd say what this is. You notice the voltage drops almost all the way to nothing. This is the effect of that limiter going off, but you still got a spike of 3 amps, and that's enough to make the starter do its job. And again, very consistent. I saw the internal resistance started to go up in both of the lithium types as they went on. Comparisons, lithium's up here. The good alkaline is up here, and then it sags down. The bad alkalines are down at the bottom to begin with. And after you've run it a second time, third time, now we're getting just the lithiums because the other ones are done. Okay, I think I've probably already said this stuff already. Alkalines are okay if you're going to use it a little. Otherwise, get a lithium. The Energizer is expensive, so go to get a Vonico or a Tenergy or something from Amazon. And test your setup if you're going to do lithiums in your, especially with the limiters.
Okay, Bernard, you're out of time now.
Okay.
So maybe you can just leave these up as follow-on, or maybe some of this will
leave
come
that
up
up.
in the
Yep.
question. Might come up
Yep.
in the questions. So
Yep.
I will ask Sean to go first this time for the questions.
Okay. I'll look at the screen that I don't see you on, so that yeah. Go ahead, Sean.
Okay. So my first question, I want to make sure that I understand correctly. Why 9 volts and not any other thing on the market?
Well, it was mostly riffing off of what Martin Quancy had done. And as I say, along comes this 9-volt controller. And I thought, well, heck, I can learn a little bit about this. As you notice in the follow-on screen, another place to go is AA's because of electron beams and the eye launch that's coming would be a place to go look. But it was just sort of, I was latched onto what he did and thought I just extended was really the driver.
Gotcha. And the 9-volt controller you showed is a currently available product, correct?
Yeah, yes, this is the Aerotech phaser that or Quest phaser that Gary was talking about last night at the
Got it.
Manufacts.
Um,
Available in November. Yeah,
got it.
sorry.
No problem. Um, what led you to, obviously you said the data logger was what you had, but what led you to the design of the rest of your experimental setup?
Well, I knew that it had to be an intermittent load. It's not just putting a thing on a resistor and draining the battery down wouldn't tell us what we needed to know for this kind of duty. Because when you're launching rockets or when you're doing deployment, and Mr. Quancy also acknowledges in his hand tests that are in that TRF thread that I linked to in the report. So I needed some way to have an intermittent but repeatable loading case, and that's how I came up with the fire and igniter, wait 5 minutes, run this thing that did about a 5-minute separation between simulated firing and so on, trying to keep it. 5 minutes is too fast for a launch controller for real, but it's still better than just sucking the battery down with a constant current, say, and made it doable in a reasonable amount of time. So it was kind of a compromise between realistic case and not taking years to do the tests.
Got it. And I've got one more. Based on what you found,
Yes.
from an economic standpoint of buying a good alkaline versus buying one of the lithium ones, what do you find is more cost effective between the two?
That would depend on your use case, I think. If you were going to just use this controller to go to the park with your kids or your grandkids once every 6 months and fly 2 or 3 rockets, probably an alkaline would be fine. If you're going to use it more, I would definitely go with the Amazon Basics or the Tenergy or the Monaco Lithiums.
Mhm.
And that also has the advantage of having a longer shelf life. So even if you put the controller away for 2 years and come back and use it again more, it would probably be more likely that it would still work.
Do you have a feel for lack of a better term, cents per launch for your batteries?
I thought about calculating that out, and I probably still could, but it would be a moving target, of course, because the prices are changing like crazy. I owe you a number for at least for battery types, I think, for that, because I think that would be a useful metric. And I basically just ran out of time before the report was due to go do that. But
Got
that's
it.
something I wanted to do.
Okay. Joyce?
Yeah, okay, let's go with Ryan next. Ryan?
Yeah. Well, thank you. That was an awesome report. I really enjoyed reading it. I liked your presentation. My first question is, I couldn't find this in your report. Maybe it was there and I just overlooked it. How many of each brand and model did you test? I guess the question is, did you test more than one of brand X, model Y?
Okay, so there's another piece that I didn't even mention. I originally designed the intermittent or the repeated test to use an electronic speed control to feed the resistors. And I found out after I'd run a bunch of testing, including on 2 samples, most of the cases of each type, that it wasn't doing quite what I thought it was. And that made me switch like a week before the report was due to the servo switch. And then I reran the ones that I thought would be representative. So that's a long-winded way of saying, yeah, 2 or 3, but the results are not directly comparable, the older tests to the newer tests. The main difference was how long the resistor was on when it was commanded to be on, and the things would shut down under voltage. I set the test to terminate if the battery fell below 2 volts, and that was happening a lot with the server with the electronic speed control based version of the test. As I say, I just ran out of time to do it all over again. because of the deadline on the paper.
Okay, I have two more hopefully quick questions.
Sure.
First was, I didn't see that you listed, what was the cost of this Hyperion e-meter? I mean, obviously you had it, it was equipment you had, you listed the equipment, but what was the cost?
So when it was released, it was $100 plus the units. They're still available from one vendor, and they're giving them away. They're like $7.
Oh, nice. Last question is, did you measure any STES igniters to verify STES's claim on the resistance of the igniters?
I did as best I could. My volt ohm meter is not the best at measuring resistance, and so what I did is I put the two probes together, see what it said, because when it was supposed to be 0, and then hold the igniter and then go back and to kind of establish a value for that. And I did that for this pair of power resistors as well. And they're to the best of my ability to measure it, they're pretty darn close.
Okay. All right. I'll pass it back to you, Joyce.
Okay, I'll just ask one quick question. Did you check the expiration date on all the batteries that you tested, and were they all fresh when you started?
So all the ones that I bought were current stock, and most of them have dates on them that are 7 or 10 years out.
Okay, that's
The
good.
ones that Martin Quancy sent me were about a year older. But there again, they claim 7 or 10 years of shelf life. So I'm sure that's a factor, but not a major factor.
And he hadn't used them before he
No,
sent
he
them
sent
to
me one. When you buy these from Amazon or something, you have to buy 2 or 4 or 8 at a time. And he sent me ones he had not also tested.
Okay. All right. Well, maybe I'll ask this one. The e-meter draw, you said you had to put it on there and let it settle for a minute. Was that draw significant compared to what was in the battery, or is it just totally negligible?
That's another thing I wanted to try and figure out a way to measure. But just based on how much the voltage dropped and how quickly it settled back down, I'm guessing it's drawing maybe 5 or 10s of milliamps
Okay,
through
that's
the
pretty
sampling.
negligible. Okay. All right, great. I want to go on quickly because I've got like 1 minute here for the audience. And Bernard, if there are more questions in the chat, maybe after your talk, you could just try to answer them in the chat if you need to.
Okay.
But let me ask a couple. One of them is from Ethan, and he asked if you thought about testing a nickel metal hydride battery.
Well, that, as you said, maybe on the screen there, it says follow on. Rechargeable batteries would be another rabbit hole to go down. So yeah, I thought about it, but certainly for the 9-volt case, it's probably not a good choice. But for other, and I've got some experience with those from my airplanes days, but yeah, so yes, but for this application.
All right, and I think the next one is, let's see, from Ed Chess, and this one may have been answered by Bob Kaplow already. Why are you discussing quad batteries when they must have 6 cells? And it looks like quad AA is just quad A. I think that was answered. So go ahead.
Yeah, that's a quad. No, did I say no? 4 cells on this follow on. Yeah, for I didn't see. I should pull the chat up and see what that's.
Yeah, why don't you answer that one in the chat, because I'm not sure what they're asking. And Bob Kaplow also wants to know where he can get one of those $7 meters. So you should tell him that in the chat as well.
Okay. All right. I will do that.
Okay, so I think we're out of time, but thank you so much. That was very useful and interesting. So now I know what kind of batteries not to buy for my launch controller. So
Yeah,
okay.
or your deployment computer.
Yeah. All right, so we're going to go on to our third speaker here, and this will be Tom Fetter. So Bernard, you need to stop sharing, and I believe Tom already is a co-host unless I messed up.
Okay, yeah, I can't share yet.
Okay, let me make you a co-host.
Okay, got it.
Okay. So you can go ahead and share and get
And you can see the slide?
Yeah, it looks like it's on full screen, I think.
Okay, should be. Okay, well, good afternoon. My name is Tom Fetter, and my report is on the rotational dynamic stability of model rockets. Okay, back in 1968, Gordon Mandel wrote a series of articles in Model Rocketry magazine on the fundamentals of dynamic stability. He later published an expanded version of that in the book Topics in Advanced Model Rocketry. And Gordon's work focused on the rotational dynamics equation that describes a rocket's response to a perturbation such as the step in the wind velocity that it sees as it leaves the launch guide. That's a second order differential equation that's typical of what describes a lot of physical systems. Now, I started studying Gordon's work back in 1999 when I was putting together a flight trajectory and rotational dynamics model. But when I took the parameters for a typical model rocket or a high power rocket and put them into this rotational equation, the result shows that a rocket would rotate with very high levels of oscillation over the entire flight. And yet, and that would be a marginally stable system. And yet we know, observing a lot of flights, that yes, indeed, the rocket does rotate as it leaves the launch guide, but that those oscillations die out relatively quickly. As a matter of fact, in a lot of flights, unless you know what you're looking for, it's even hard to see the oscillation of the rocket. Now, this is from an actual flight measurement. So the purpose of this paper was to understand why is it that a rocket is so much more stable than the rotational dynamics equation alone predicts. Now, the thing that describes how quickly these oscillations die out is called the damping ratio. The damping ratio is calculated from the parameters of the rotational dynamics equation. And the larger the damping ratio, the quicker the oscillations die out, the more stable the system is. And so the damping ratio is the key indicator of how stable a second order system is. So the flight models that I was building both a 3D flight model and a 2D flight model for looking at the dynamic stability. If you assume that the rocket is not spinning, the 2D flight model is adequate. And the 2D model consists of two equations, Newton's equations, that describe the motion of the rocket along the x and the z axes. And then it includes the rotational dynamics equation, which we just saw. And then the last part of the model is the part that maps between the rocket frame of reference and the ground or inertial-based frame of reference. And in the two-dimensional model, that's simply the angle of rotation of the rocket. In the 3D model, this is actually Euler's equations. And this is a set of it's a simultaneous nonlinear differential equations that you can't solve in closed form. You have to solve them numerically. I use MathCAD to do that. It has the tools built in necessary to solve those equations. And when you solve it, you get a result that looks a lot more like you'd expect, where the oscillations die out very quickly. So the question is, why is it that when you solve this set of equations together simultaneously, you get a result that looks a lot different than when you solve the rotational dynamics equation all by itself, assuming just a fixed step input? And the answer has to be that there must be coupling between these equations. Well, being a model, you can zero out all the terms you want to see which ones are actually causing the coupling. And if you zero out everything but the thrust force and the x-axis lift force, you get a result that looks very similar to what you get than when you solve all of the equations together. And so from that, since we know that the thrust force is an input to the model and that that's fixed, that's a fixed value of thrust, that the coupling must be coming from the x-axis lift force, and it must be going to the input to the rotational dynamics equation. And if we plot this input, we see that it actually has a small sinusoidal component to it. And that we see that that sinusoidal component is 90 degrees out of phase with the rotation angle of the rocket. And we know that in a second order differential equation, that the second order is the first order term that provides the damping to the system, and that first order term is 90 degrees out of phase with the zero order term. So that gives us some clue that this little sinusoidal component is what's providing the enhanced damping to the system. So what is the input to the rotational equation? Well, it's simply the rotation angle of the input of the oncoming airstream. The rocket wants to align itself with the direction of the oncoming airstream. And that angle is simply the arcsine of the total velocity of both the rocket airstream due to the forward velocity of the rocket and the wind velocity divided by the total airstream velocity. And you can linearize that for small angles, and you get two terms, one due to the x-axis velocity of the rocket and one due to the wind velocity. And is going to be that x-axis velocity that is actually coming from the x-axis equation. So what we're looking for is a small sinusoidal component in this x-axis velocity that we saw in the last slide. So to find that, when a rocket leaves the launch guide, it sees the oncoming wind, so it rotates into the direction of the oncoming wind. And once it has rotated, there's a component of the thrust that's pointed along the x-axis, so it causes the rocket to accelerate. The flight path actually accelerates along the x-axis. If we look at the x-axis velocity, we see that it indeed increases up until motor burnout, and then it decreases slowly due to drag. And sure enough, we can see superimposed on that, there's a small sinusoidal velocity. And so we want to isolate that sinusoidal velocity. To do that, we can create another equation and add it to our model. And this is basically a copy of the x-axis equation with both the thrust and the drag force set to 0, leaving just the lift force, which is what's the source of this sinusoidal oscillation. And we solve this equation simultaneously with the other equations in the model in order to pick up the total velocity of the oncoming airstream. And what we get is just that small sinusoidal velocity in the x-axis velocity. Now, the damping in the rotational equation comes from the first order term, which is proportional to the rotation rate of the rocket. And what we want to do now is to compare the phase of the rotational damping to the phase of the side-to-side velocity that we just found. And the way we're going to do that is we're going to translate the rotational velocity into a tangential linear velocity. And we're just going to pick an arbitrary point to start with. We'll pick the center of pressure. And what we're going to do then is to determine what's the tangential velocity at the center of pressure due to the rocket's rotation rate. So to do that, we simply multiply the rotation rate times the distance between the center of gravity and the center of pressure. And that gets us the velocity of the rocket tangential to its rotation at the center of pressure. And if we plot that along with the side-to-side velocity term that we just found, we see that the two indeed are in phase as we'd expected them to be. We also see from this that the side-to-side velocity is actually 4 times larger than the tangential rotational velocity for the rocket that we're looking at right now, which is that our test rocket that I have used throughout the simulations and in some of the tests that I'll present at the end. So the damping, the rotational damping comes about because as the rocket rotates, it has a tangential velocity that's tangent to the oncoming velocity of the total airstream that creates an induced angle of attack. That angle of attack creates a normal force that opposes the rocket in the direction that it's rotating and provides the damping to the system. And this side-to-side velocity then simply adds in phase with the tangential rotational velocity to increase that effective angle of attack to provide the enhanced damping. So we have an enhanced damping term. And if you go through the math, what you find is that the gain that both the tangential rotational velocity and the side-to-side velocity sees is the same if you pick the point of reference for that tangential velocity as the center of pressure. Now that wasn't expected, but is a really interesting result. But what that also says is if you're going to have enhanced damping, that it has to come about because the side-to-side motion is larger than the tangential rotational motion. Okay, so this is what the overall motion looks like. And the blue trace traces out the path of the rocket due to the small sinusoidal motion. And this is just the small sinusoidal part of that. Keep in mind that the overall rocket at this point is actually turning off to the left, turning into the wind and moving off to the left. And then superimposed along this path is the angle of the rocket at each step along the way. Now, in this graph, the x-axis has been expanded by a factor of 1,000, and the rotational angle has been increased by a factor of 10 to allow you to actually see the motion, because the motion is actually very, very small. And it's easiest to see this in a video simulation. So if we look at what's going on as the rocket is sliding to the right due to this side-to-side motion, the tail of the rocket is rotating to the right. And as the rocket slides to the left, the tail of the rocket is also rotating to the left. So the two motions add together in phase. And if the motions are in phase, the velocities are in phase. So that's what's going on. Okay, so the mechanism for this stability is the fact that the rocket rotates. When it's rotated, then the lift force causes the rocket to move to the side. So that side-to-side velocity term then provides the damping back to the rotational equation. So that's the mechanism for the enhanced stability. Now we want to quantify the enhanced stability. The original model, the equations were nonlinear, and the reason they were nonlinear is because the coefficients included a copy of the velocity of the rocket. But if we fix the velocity at a constant, then that linearizes the equations. And with some manipulations, you can actually roll them together into a single second-order differential equation, which I call the coupled model. And after some math, you can now create a damping ratio that includes the effects of both the tangential rotational damping as well as the side-to-side motion of the rocket. And by the way, I want to say at this point that Edward Labuddy in his 1999 NARM report actually came up with this exact same expression in his R&D report. He took a different approach to getting there, but came up with exactly the same answer. And if you plot a second order differential equation using this damping ratio and compare it to the output of the complete model, which is in red, you see that the decay of the oscillations of these two match very, very closely. Now, the complete model also includes the effects of gravity, which adds a gravity turn to the flight path, which isn't in the linearized equation, but we're not interested in that part. We're just interested in how quickly does this die out, because that indicates the stability of the system. And if you compare that to the uncoupled damping ratio, you see that significantly underpredicts the stability of the system. And the difference in the damping ratios between these two is a factor of 5, and that's a really big difference. Okay, so this is a really complicated equation, and it's hard to look at that and say, okay, how do my various rocket design parameters impact the stability of the rocket? It's just too complicated, at least for me, to wrap my mind around. So in that case, what we do is a series of what are called sensitivity analyses, where we look at the sensitivity versus various rocket design parameters, such as the nose cone weight mass. We add nose cone weight to stabilize a rocket, the body tube length, the fin size, and the material density. And so what we're doing in each of these cases, and this is just an example of changing the mass that we add to the nose cone, we're going to look at what the stability margin is versus the nose cone mass. And as expected, it increases, the stability margin increases as we add nose cone mass because we're moving the center of gravity forward. And the uncoupled damping ratio predicts that as we add nose cone mass, the rocket becomes more stable. But the coupled damping ratio has two differences to it. First, it's bigger than the uncoupled damping ratio, as we'd expect, because we've shown that the system is going to be more stable, and that comes with a larger damping ratio. But the other interesting thing is that it moves in the opposite direction of the uncoupled damping ratio. So what this says is, as I increase the nose cone weight mass, the rocket actually becomes less stable. Well, why is that? Oh, to say that you get similar results when you look at the sensitivities to body tube length, fin size, and material density. There's not a direct correlation between the traditional measure of the rocket stability margin, and the direction that the coupled damping ratio moves. Okay, so why does it become less stable as you increase the nose cone weight mass? Well, the coupled damping ratio is made up of two terms. First, it includes a copy of the uncoupled damping ratio, and then it has a second term that comes from this side-to-side motion of the rocket. And the reason it becomes less stable is because of this particular ratio that actually decreases with increasing nose cone mass, and it decreases faster than this term increases with increasing nose cone mass. So the net sum of the two actually decreases. Think of this term as the term that describes how easy is it for the rocket to move side to side. And what it tells us is that as you increase the nose cone mass, that it reduces the ability of the rocket to move side by side. And that's the side to side motion that's providing most of the damping to the rocket. We can show that in this case, we've got two examples, one that's more stable, one that's less stable. The more stable has the lighter nose cone mass. The less stable has the greater nose cone mass. And in the more stable system, the oscillations in the step response die out faster than the less stable system, but the side-to-side amplitude of the velocity is larger in the more stable system, even though it dies out faster than it is in the less stable system. So it's this larger magnitude side-to-side motion, again, that's providing the stability to the system. Okay, so to prove the model, we need to actually show that this thing is real. Can you measure the side-to-side motion of a rocket in flight? So to do that, I used a board called the RAF data logger. That was the board that was originally developed for the RLS flights. It includes an accelerometer and gyroscope. We use the accelerometer to measure the side-to-side motion and the gyroscope to measure the rotational velocity. And after a fair amount of mathematical manipulation, you can get from that the x-axis velocity. And we can see that it looks a lot like the simulation. And you can see the little side-to-side motion superimposed. So to extract that side-to-side motion, what I did was to use a polynomial curve fit, and you pick the order of the polynomial so it's high enough that it can follow the slow change in the x-axis velocity, but low enough in order that it can't follow the more rapid oscillations that we're trying to pick off. So it acts like a low-pass filter. And when you subtract that curve fit from the total data, you're left with just the side-to-side velocity. And what we need to show, is that the phase relationship between the side-to-side velocity and the rotational tangential velocity is in phase, which it is. And secondly, that the magnitude of the velocity is about the same as what we saw from the simulation, and indeed it is. Now, in this case, we're plotting not the velocity, but the actual distance traveled to show you how small this really is. And the side-to-side distance is less than 2 inches. And so it's a really small distance, but it's enough to stabilize the rocket. And also keep in mind that this 2-inch side-to-side motion is occurring while the rocket is simultaneously traveling about 100 feet during the upward portion of the flight. So it's a really small portion of the x-axis motion. Okay, so quick summary. We showed that the side-to-side motion leads to its rotational stability. The greater the stability, the greater the side-to-side motion. The coupled damping ratio is greater than the uncoupled damping ratio, as we'd expect it to be. And the stability is not directly correlated to our traditional notion of stability, which is the stability margin, the distance between the center of gravity and the center of pressure. And then lastly, we showed that the magnitude and the phase of the modeled side-to-side motion agrees with the flight data. I'd like to thank people I need to acknowledge: Gordon Mandel and James Berriman, whose work inspired this work, and Kurt Gunther, who graciously read the draft copy of the paper that this report was based on and offered a lot of great feedback to me. So open up to questions.
Oh, thank you very much. That was really a lot to cover in 20 minutes, and you did an amazing job. So, and there's lots more in Tom's report, which will be on the web, the NAR webpage for under R&D reports later. Tom, I'm going to start with the first question. You had some next steps, and one of them was to go to 3 dimensions. And maybe you can describe what that might mean. What does it mean to model in 3 versus 2 in this kind of a scenario? And then what do you think is going to happen? Is it going to just negate everything you've done and you might balance each other out and there's really no effect, or do you think it's going to make things even more stable?
Yeah, like I said in the beginning, the limit of this analysis is that it's done in 2 dimensions. So it assumes that the rocket's not spinning. And I've shown in a number of flights that I've measured that that indeed is the case. What it wouldn't cover is the case where the rocket spins up for some reason. And when it spins up, then it goes through the motion called coning, where it, because there's coupling between spin coupling between axes, the rocket moves in a kind of a coning motion. That is another artifact of stability in and of itself. So what this model covers is a rocket that doesn't spin enough to go through the coning motion. The spin model wouldn't invalidate this. It simply would allow you to investigate another dimension of stability associated with coning.
Is that something you plan to do in the future?
Yeah, I have measured a number of rockets in flight. What I found is that as a rocket, as when you're close to motor burnout, rockets tend to spin up, and my theory on that is because of the fact that basically the residue of the motor burn gets caught in the nozzle, and it causes an off-axis vector that causes the rocket to spin up at motor burnout. And at that point, that's where you see the coning. And that's Gordon Mandel actually did a lot of work looking at the spin coupling. That was a big part of what his stability analysis was about. He didn't have the ability to actually measure rockets in flight because instrumentation didn't exist back then to actually measure real rockets. And so I think that's the next step for where I'm going to be taking this work.
Okay, thank you. Sean, would you like to go next?
You're on mute.
I can't hear you. You might be muted, Sean.
So now that you can hear me, we covered a lot of mathematical theory very quickly there, and I'm not too proud to admit that my differential equations is pretty rusty. But from the standpoint of someone who does a lot of flying and perhaps a little afraid of differential equations, where do you think that you can pick up this information and run with it as a flyer, perhaps? I mean, especially designing high energy systems like high power rockets, where this is very important to know how they're going to perform.
Yeah, I think the important thing is to have rules of thumb, and we've always gone with the rules of thumb, such as you need to have at least 1 caliber of stability margin to ensure that your rocket is going to be stable. And none of this work invalidates the work of Jim Barrowman and that basic recommendation for entirely different reasons. What this says is that if you have more stability margin, the rocket actually becomes less stable, but the amount that it changes isn't a lot. But you might infer, well, maybe I want to start running rockets with like a 1/2 caliber of stability margin. You don't want to do that because the stability margin does move with angle of attack, especially on longer rockets. So that's what I mean here by the second bullet, which is looking at some new rules of thumb for recommendations around how many calibers to use. And I think as Jim Jarvis mentioned in his report, he thought it might be something rather than recommendations on the stability margin based on body tube diameters, you would follow more the length of the rocket, because longer rockets, the center of pressure moves forward further. So I think that there are perhaps other refined rules of thumb around stability that would take into account both this work and the fact that the center of pressure does move forward versus angle of attack.
And as always, it's an incredibly complex system that you can push and pull in many ways.
Yeah, absolutely.
On that line of thinking, our earlier presenter was talking about torque to go in the direction away from high power. Do you see this being something that would be applicable to precision, or knowing, like being able to predict and be consistent with your models?
So I'm
Or
not
do
sure
you,
I quite understand the question. So Edward Buddy back in 1999 did a report on maximizing the altitude of your rocket and came to the conclusion that as you make a rocket truly more stable by reducing the calibers of stability margin, like you flew a rocket with really small fins and about half a body tube diameter of stability margin, you got the maximum flight. So I think there are things when you're trying to fine tune to competition, there are things that come out of this that would direct you toward perhaps slightly different rules of thumb than we're running under today. Like, how do you get that last foot or two of altitude for a altitude competition model rocket that's not a really long rocket? It's a relatively short rocket where you can afford to run with a smaller stability margin and actually stabilize your rocket by doing that. You still don't want to cross over. You never want your center of pressure to cross your center of gravity, because then you get a pole in the right half plane, the system goes unstable. And another part of the report that I didn't have time to talk about here was this thing called root locus that shows more graphically what happens as you move your center of gravity ahead of the center of pressure, behind the center of pressure. The stability of the rocket changes extremely rapidly. So you never want to get close to the zero stability margin.
Got it. And for background, what is your background that you brought into this to give you the skills to do this math? Is it something you've learned on your own, or is it a professional thing for you?
So, I'm an electrical engineer. I'm a retired engineer. I was trained as an electrical engineer, but so my interest in aerodynamics is more as a hobby interest. But a lot of the math that is used by aerodynamics is similar to the math that's used in electrical engineering. So, a lot of the core training is similar in terms
Very
of the
cool.
mathematical tools.
Okay, I'm ready to pass it on.
Okay, go ahead, Brian.
Awesome. Well, thank you very much, Tom. This was an awesome presentation. I really enjoyed it. I found it fascinating. I enjoyed that you I really liked that you had the data models, and then you also did the flight data. I had some questions about your budget. The first question I have is you listed 3 H-128s. Did you do 3 flights? I couldn't tell from the data if you did 3 flights.
Yeah, I did fly that particular rocket. The TR-1, I flew 3 times. I only
Okay.
presented 1 flight data's worth of data here because it takes so much to present the data. The other 3 flights were very similar results.
Okay.
I think to validate the model, you need to test it over a wider range of rocket configurations. It actually took me 5 years to find that side-to-side motion. I had been flying the RAF data logger for 5 years in other rockets before I could convince myself that I actually saw the side-to-side motion. And it took a purpose-built rocket to do that, where I mounted the data logger near the center of gravity. I can go in later why that was, but it took a purpose-built rocket, and it took a long time to find it. That was really the biggest challenge.
The next question is what are the 2.2-inch bulk plates? You list that in your budget, but I couldn't figure out what that was. Was that just how you mounted the logger at the CG?
Well, those are just the end caps. Those are these.
Okay,
These
got
are
it.
the end caps on here. The sled is 3D printed, and these are the bulk plates.
Okay, excellent. And then the final question I had for you is, obviously you leveraged a lot of prior art here. You leveraged the Berryman equations. You leveraged a report from the late 1990s. Could you kind of quickly just kind of go through, like, what do you feel is your original is your original portions? That is it just that that section that you added for the side-to-side motion component?
Well, yeah, actually, I didn't learn about Edward Buddy's work until after I actually completed all this work. And thanks to Gordon Mandel, who pointed it out to me, I went back and found it. The original contribution to this work, a couple of things. The main part is finding the side-to-side motion component. Is that side-to-side motion that is why our rockets are so stable. And so that's, at least as far as I know, this is the first time that I've seen that. And then doing the sensitivity analyses, Edward Labuddy came up with the same expression for the couple damping ratio, but he didn't take it in the direction of saying, okay, now what? What does that mean? And not looking at what are the sensitivities to rocket design parameters? How can you affect the stability, the couple stability of the rocket?
Awesome. Well, I think we should probably jump to the questions in the chat
Yeah.
now. Joyce, you want to run that again?
Yes, we're at 4:30 and we've used up our time for this session, so I think we need to move on to our next speaker. But Tom, you could look at the chat and maybe you could answer the questions that are in the chat directly.
Yeah, I'll do that.
There's about 3 questions there about the equations, how you solve them, and how do number of fins affect stability. So we'd like to hear the answers, but maybe you could type them in. That's
I will do
great.
that.
Thank you. Okay. All right. So we'll go on next to Steve Morris. Steve, I think you already are a co-host.
I will try. Okay. Everybody can hear me. I will try to share. No, host disabled. I can't share
Let
yet.
me try it again. Okay.
Yep. Now I got it. Okay. One participant can share. Okay.
Okay, we can see your slides. We
How
just
does that look? Okay. And
we
I'm
need
going to
full-
try.
full screen. Yeah, that's good.
Okay. And I'm going to try to use the laser pointer. Can you
Yes.
Can you
We can
see a red dot?
Yes.
Okay, so very good. So thanks for the opportunity. I am the official title of my project was The Effects of Venting Altimeters on Rocket Airframe Transition Sections. And it could also be called something along the lines of what would the consequences be if you completely ignored traditional wisdom and vented your barometric pressure sensing altimeter on a transition section. And by that, I mean that traditional wisdom is to keep your vent holes away from transition sections and obstructions on the airframe and keep them in clean airflow. So with that, I've got about 25 slides and I am going to kind of power through. Here's my agenda, an overview, a rocket overview, a test flight overview, a data overview. I won't really go into all the graphs ad nauseum, but and then some conclusions. Not to, just in case I get over on, well, okay, yeah. So the thesis statement boiled down to, it matters where you place the vent holes for barometric sensing altimeters, or does it? And by that, I want to go right into 2 of my conclusions. On the one hand, what I found was vent holes placed on transition sections had little to no impact on actual recorded apogee altitudes compared to traditionally vented altitudes. They were within what I considered to be a pretty remarkable agreement. They were within less than, about 0.25% agreement when compared. And you'll see that data as I go through. The other conclusion I came to was that that said, the vent hole placement did result in noticeable differences in data during the fastest parts, the coast and the boost phases of flight. So that's the two are I think you're going to see those in the data. In terms of an overview, I built a payload section that had altimeter chambers to house simultaneously 3 commercial data logging altimeters. I chose Perfect Flight Peanuts, and I purposely made each chamber size-wise, it was identical, and I vented them similarly and yet differently. I wanted to make the chambers identical in order to reduce variables between the for the purposes of the test. I launched all 3 altimeters on each flight, and so was collecting data through all of that. But I had 3 separate chambers. They were sealed and they were identical in shape and size, but one was my control chamber, the top one. So as we go down from the nose cone down to the fins, the top chamber was the traditionally vented control chamber. The second, then down from that, as you'll see in photos later on, the diverging transition chamber was from a BT60 to a BT70 airframe, and that was the middle chamber. And then the bottom chamber was a converging transition chamber, BT70 to BT6, back down to a BT60 basically. And you'll see that in the images. I flew 6 flights, and we'll go over those flights. And but I purposely chose a range of motors to give some faster speeds and some slower speeds to try to tease out some of that information. Okay. So here is an image of the completed rocket. I've added toothpicks for visual cues for the purpose of the photo. It doesn't actually fly with these toothpicks sticking out of it. Those are stuck into the vent holes for each of the chambers. So you see 3 up top here. That's my control. Those are the traditionally vented. They're about 5 calibers down from the nose cone, and that was my control chamber. And then right below it, you see the BT60 to BT70 diverging transition, what I call the diverging transition. That's the middle chamber. And then you've got a section of BT70 airframe, and then below that you've got the bottom chamber, and you've got the toothpick sticking out of that. So again, the conventional wisdom says, put 3 or 4 holes, vent holes. So I chose 3 for this purpose. And then in addition, then you've got just the rest of the rocket. The rocket stands about 4 feet, weighs a little over 400 grams typically, and it's got a 29 millimeter motor mount with, and I had to adapt it down to 24 for some of the flights. Okay. This is a closer up of just the payload section, and you can see a little bit clearer the toothpick sticking out. So the vent holes were purposely designed to stick straight out of the basically perpendicular to the surface of the airframe. So this toothpick here is perpendicular to the airframe. This toothpick is at an angle. It's about a 10-degree angle, and it's perpendicular to the surface of the transition. And then this one is equally angled, again, 10 degrees. The transitions were geometrically identical, and so it's 10 degrees angled down. The other thing on this photo that is noteworthy is that the in-flight, that this was one of the other vent holes. All the vent holes are line up as you go up the airframe, so they're all in the same kind of air path. So that was intentional. Okay, so here's an expanded view of the same thing, and here you see the clear plastic altimeter chambers in each of the sections, and you see the black number 7 rubber stopper on the one end of the chamber that is used to bring the peanut in and out. And so that was the other end, and again, it's a plastic tube, so it's sealed. The other end down here you'll see it in a later image, is also sealed. So the only air path in and out of these chambers is through the vent holes, and the vent holes are about a 1/2 inch length of hollow brass tubing purchased at a hobby shop with specific dimensions, and I use the same tubing on all the chambers. So the intent again was to reduce the variables so that I could compare the data from one altimeter to another altimeter on the same flight. I wasn't so much concerned about comparing data from altimeter to altimeter in between flights. It was just that the one flight I should be able to compare the top altimeter data to the middle one and to the bottom one. So that's what you see here. Everything fit together. Here is the same. Here's the same transition sections under construction. You can see the black or the clear plastic tube, 4 inches long, 1 1/4 inch in diameter, and the peanut inside. It is sealed on the bottom. These are actually candy, holiday candy cane kinds of things, and I just used the bottom half. That's sealed, but in addition, if it wasn't sealed, I actually and you can see it in this image on the right. There's epoxy down at the bottom in the hole that I hogged out in the balsa to further seal. In addition, you can see the 3 hollow brass tubes sticking in, separated by 120 degrees, and these entranceways were also sealed with epoxy around each of the brass tubes. So really, I was quite satisfied that between the rubber stopper, the epoxy, and the clear plastic nature of the altimeter chambers, the only way in and out of these chambers was through these vent holes. Okay. Here's just a close-up of the completed ones, and again, you can see the stopper, you can see the clear plastic tube, you can see the vent hole, and again another view of the toothpick there. Basically, in that degree, that's about a 10-degree down angle or up angle, depending on which transition it is. And you see the control over here on the left. Okay, so all three altimeters were loaded with peanuts for each flight. So in terms of test flights, I did a total of 6, each with all 3 peanuts, the same peanuts. I borrowed one, I'm sorry, I borrowed 2 and I owned one. And so that was, I used the same peanuts, and I did bench test them prior to confirm that they were tracking in terms of they were actually remarkably in sync when I bench tested them through a homemade pressure chamber. The boost and recovery for all of the 6 flights was generally nominal. Deployment was after apogee. I did have a tree recovery on flight 4, and flight 5 was purposely, the motor on flight 5 was the slowest. It was an E30-7, and it was a little bit windier that day, and it did weathercock. So you'll see that, the consequences of that in the upcoming slides. I did 3 flights. The first 3 flights were actually on the same motor, an F30-6, the same afternoon, same weather conditions, so that actually within about an hour and a half of each other. So that actually worked out really well. And on those 3 flights, I rotated the peanuts between the chambers in order to further tease out if there were any peanut dependencies. Because I wasn't testing peanuts, I was testing the venting that the peanuts were, were being given air by. So the peanuts were initially rotated, but I didn't end up rotating the peanuts in subsequent flights. The range of motors, I purposely chose impulses ranging from slow to fast, and that worked out pretty well. The E30 had the slowest at 33.5 Newton seconds, and then an F50, a CTI F59 at 57 Newton seconds. So you'll see the data tracked with that. I won't go into this other than to say this is the type of this just for completeness. This is basically the information from flight 1. This is the information from flight 2, and you see that these were the numbers that were beeped out from the peanut at the end of the flights. And I did convert, just so as a note, the peanut beeps out miles per hour when it beeps it out, but I converted all my velocities, all my speeds are in feet per second. So I converted those beeps to feet per second. So you'll also see that the middle you'll see the rotation of the actual altimeter number reflected in this, or the first 3 flights where I just cycled them through each of the chambers. But then I did not do that for the other 3 flights. So this is a curve this is a graph that shows a lot of the data. It's basically this set of bars is flight 1, this set of bars is flight 2, and so on. This is where I come up with the conclusion that the flatness of these lines, and here are the numbers, 805, 807, and 807, those are the apogee altitudes for flight 1. The data, any data collected out of the top altimeter, the control altimeter, was graphed or charted in red. The middle altimeter was graphed and charted in black, and the bottom altimeter was graphed and charted in blue. For completeness, I also included the open rocket estimations for each of these flights. So just noteworthy, flight 4, all 3 altimeters reported 770 feet. So they were identical. The difference was 0. Flight 3, on the other hand, the difference was 7. That was the other. So those are the two outliers. One was perfectly in line, and the other had a difference of 7 feet. This is your E30. This is flight 5. You can see that open rocket simulated it a lot higher. The weather caulking just didn't allow that particular flight to reach its full potential because of the slowness of the E30 coupled with the wind that day. Okay. So this is representative of the type of peanut curves we've seen. Most of us have seen a lot of these. This is flight 2 on an F-30. You can see, so this curve, when you first look at it, you might think, okay, that's pretty standard. It's actually 3 curves. It's red, black, and blue. It's the top, middle, and bottom. And so I look at this and I go, wow, that it really matches up quite nicely. The area I'm going to focus in is the boost and the coast phases, because those are the fastest parts of the flight, and those were where I thought the interesting things might be happening around the transition section. So here is the exact same data. This is the first 10 seconds, just basically zoomed into the first 10 seconds. And you can see that the 3 altimeters were collecting, the graphs are distinct. And so you've got different things, different pressures being represented here. But you've also see that it coalesces nicely at apogee. So that's where I come up with the kind of the first supports the first conclusion that really you've got nice agreement on once the rocket slows down, and it kind of makes sense, right? The rocket is going slow, and so the speed around the airframe, the speed of the air around the airframe is not generating the pressures that you see at the beginning of the flight. So that's I've included that. And this is yet another zoom in, the exact same data, the exact same flight 2. Just I happened to pick it because it shows this stuff, and you can just see the difference between the 3 curves, and we'll get into some of the. There's another curve that shows this. So again, it's top, middle, and bottom, and this is representative of all the flights. This chart shows the first 3 flights, and you can see here, basically the top altimeter is the bottom curve. The red, the control curve is the lowest one. That the 2 transitions are both higher, and I did not expect that. But but I'll talk a little bit more about that. But so this is just for completeness. I want to show the data right around the interesting part where the rocket is going the fastest. These are nice because it's the same motor, it's the same afternoon, same atmospheric conditions, and so the data looks fairly consistent. This chart is flights 4, 5, and 6. And you can see there's a little bit more variation. Those are different days, different months, in fact, at the field, and not quite the same nice look. But unfortunately, data doesn't always work with your assumptions. This particular one, the E30 data, is the slowest flight, and it does make sense to me that the data is not that separate. That it's not going as fast, and so that's kind of an interesting thing. But if folks wanted to look at this data offline, I just wanted to include these graphs. This is the
3 minutes now.
Very
3
good.
minutes. Okay.
This is the derived speed. These are beeped out speeds from the peanut, and again, the same organization in the charts pertains here too. these are derived speeds. So this is a calculated number from the altitude. So there's going to be some noise. I actually did not end up using this to generate a whole lot of conclusions, but I did want to graph. So these are the derived speed graphs from each of the peanuts on each of the flights. And again, the convention of the red, black, and blue conveys on this one. And so you can see that there are some interesting things occurring that that are detectable in those flights. And my last set of graphs is basically it's the percent difference. And I just represented two of these. This is flight number 1, and this is flight number 6. This is the percent change from the middle and from the two transition sections, the percent change relative to the control. And you can see that during the fastest parts of the flight, the changes are actually quite quite apparent. They're almost 100%. So conclusions: the vent holes, if you're only interested in apogee altitudes, you can almost put your, well, I'm not going to say it, but you can put your, I did not find in my flights the vent hole placement on transitions made a whole lot of difference. But you can, with commercially available data logging altimeters, notice some boost and coast phase flight differences in your data. And the data, both diverging and converging transition sections, produce low pressure areas, which was a little bit of a surprise. One observation was that if you're making staging and air start decisions with a barometric altimeter, which most people aren't, but if you were home brewing your own altimeter with an Arduino and a barometric pressure sensor, you need to be careful that you're, during the boost and coast phases where you're staging and air starting, your data may very well not correlate well with simulations, with your simulations in OpenRocket or RockSim. And also just establishing sound data processing methods. I generated 36 curves. I thought that was a lot, although I see the other R&D people reports tonight generate a lot of curves as well. So, but yeah, making sure that you can keep all your numbers straight is important. In terms of next steps, leveraging some software, either ANSYS or as a result of David Carter's presentation yesterday, FreeCAD with OpenFOAM to model the airframe, the airflow around the airframe, and compare that information with the test data. That'd be a good next step. Also conducting, I used Perfect Flight Peanuts, but maybe an egg timer ion would be a good alternative altimeter to compare. In addition, repeat the test flights with vent holes, gather more data with vent holes that aren't angled. Instead, they're straight horizontal. So,
okay, you're out of time.
Very good.
All right, that's good. Okay, thank you. Yeah, thanks again to all the speakers for keeping very close to time on this. Is a challenging thing to do with these events. So thank you. Very interesting. So I think I'll have Ryan ask the first question this time.
Yes, thank you, Steve. That was an interesting report, and I enjoyed the presentation. I have a number of questions. My first question is, in the report, and you also stated just now, that the only way the air could get to the altimeter was from the vent holes. Did you do any tests to verify that was the case?
Yeah, so yeah, to some degree. I mean, I tried to pressurize, with my with a syringe, but I did not actually verify that. The rubber stoppers were pretty secure. They fit nicely. I did tape them over so they were secured, from movement, but they were pretty snug. I am fairly confident that the plastic tubes themselves were airtight, because I was only using the bottom, so they were sealed at the manufacturer, and you couldn't blow, if you just puffed in, you could not blow through. So I'm fairly confident that that my statement is reasonably accurate.
Okay. So looking at your data, it looks like on boost, it looks like the altimeter, the altimeters in the vent holes that were located on a transition were reading about 50 feet higher on boost. Am I reading that correct?
Yeah, or right, in percentages, it was about the last two graphs, basically 100, almost 100. They could be as much as 100%. They were over 100% in some cases during boost. Yes.
Have you thought about how this might affect competition flights where the only available motor would eject before apogee, for example?
Right. No, I didn't. And I did confirm through the graphs of all the flights that the motor eject was either at, I had no early ejections in any of my data.
Yeah, I noticed that as well in your report. That's interesting stuff. And then my last question is, have you given any consideration or do you think that on your rocket, the first two chambers had their vent holes relatively close to each other? The third one has that long section of straight tube before the third one. Do you think that with the holes lined up, that the first set of holes could have affected the second set of holes?
Yes, it's possible. I think that would be where I would be eager to see if a FreeCAD or ANSYS simulation software might actually inform some of the pressure or some of the airflow images around those areas. But yeah, I definitely wanted to control 5 or 6 calibers down from the nose cone. But then the transition was going to be where it was, and then I wanted to give a healthy length of BT70 to separate those ones. But yes, that's a potential.
Okay, thank you very much, Steve. If I've picked up on our pattern correctly, I believe Joyce would like you'd like Sean to go next.
Yes, I'll have Sean go next. The pattern is pretty random, but go ahead, Sean. And you have to unmute yourself. Can't hear you.
Is this better?
Yes,
yes.
I can hear you.
Okay. It was my microphone this time that was screwing me up. So you talked about apogee altitudes agreeing pretty closely because of the speed of deployment being low. Did you think about doing anything that would seeing if you could doctor the altitude for like maximum deviation, or seeing if you could intentionally do even worse than the 10-degree transitions that you were using?
So I wanted to make so if I understand the question, I did purposely want to make a payload section that was reasonably realistic. I wanted to go BT60 to BT70 because the sizes were good. I did, for example, I didn't want to go BT20 to BT80 and then back down to BT20, and which might have teased out more stuff, but whoever sees that's a weird looking rocket. I did want something that was reasonably rocket looking. So I purposely chose 60 and 70, the BT 60 and 70. If that addresses your question, I'm not sure.
It was more curiosity of like how if you were attempting to make it extreme, but I understand your purpose in trying to make it look like something that a person would actually fly, and not attempting to make it as bad as possible.
Yeah, I mean, I might have made my life a little easier had I gone to the extreme, but then it wouldn't have, then someone could say, or I could say, really, but who cares about that? Because nobody builds BT20 to BT80. What about something more realistic or more possible in terms of the thing? And if you can detect it in that situation, then one possibly could detect it even easier, or the situation would be even more noticeable in a more extreme circumstance.
Gotcha. Give my brain a minute to catch up here, Steve. the I'm not sure where my brain went with that. Joyce, can you ask a question while I
Yeah,
reboot here?
I wanted to ask, well, first I'd like to run this over just a couple minutes past 5 because there are some audience questions and Steve may not get a chance to answer them in the chat. But I like the questions in the chat. I had some of the same ones, so I want to ask a few of those. They're quick. Were the lengths of the brass tubing the same for all the altimeters?
Yep, half an inch.
Okay, were the ones in the transition sections angled a little bit compared to the ones that was in the standard one, the tubing?
Yep. They were purposely angled perpendicular so that the brass tubes are perpendicular to the surface that they are on. And so that's where the 10-degree angled. So the
Yeah,
top one
yeah.
was 10-degree angled
Okay.
up and the bottom one was angled down. But
And
the control was flat.
Do you think that angle made any difference? Or
So
would make any difference?
I don't know, but I wanted to make it standard. Whatever it was, I wanted to make it standard, and that's why I thought the next step might be. And I've already actually constructed, 3D printed this particular one. The angles are straight out, so on the transition. So that would be
Okay.
yeah.
That's kind of what I'm thinking. Yeah, it's great. You thought ahead to do that. And then Ethan asked, do you think your conclusion would apply to vent holes on a nose cone?
Yeah, I mean, a nose cone is a transition. And so I would think that it's a transition from 0 to whatever the body tube is, right? And so there could be applicability to transitions depending on where on the nose cone. But yes.
Okay, and you might look in the chat, there's some discussion about standard vent hole sizes versus and common rules of thumb versus what you used and whether your vent holes are large enough.
Yeah.
But yeah.
I think these were generous vent holes, especially considering the size of the chamber. The chamber was kind of small. These vent holes were very generous. But yes, I'll look in the
Okay.
chat.
I want to get back to Sean before see if he recalled his question.
No, it went straight out of my head, Joyce. But thank you.
Okay. Let me look through the chat here for just 1 second and see if we've answered all of these questions, or if audience, if you have any more questions, let me know. I think we've mostly answered them. Yeah, okay. Oh, Jim Filler asked, how did you select your vent hole size?
It was what was available at the hobby store. Again, it's this brass tubing, this hollow brass tubing.
Yeah.
In the report, I have the actual inside and outside dimensions, but it's yeah.
Okay, so just what you could find, right? Okay, well, let's see, there's maybe one more new message here. Jim says, thank you, okay, or he's happy with your answer, okay. All right, so I think that concludes our R&D, and I think it was very successful presentation, so thank you all. And tomorrow at today, Sean and Ryan and I are going to deliberate, and tomorrow we will announce the rankings, and in A and B division, well, B division's only one, but it was great. So, and we do have a small budget for cash awards. I don't think we're going to announce the actual amounts of cash, but we will email you with that information. And I will also talk with Todd about getting the final copies of the R&D reports on the website. If you did see any typos in your report or want to update, please send us the latest one. And maybe there'll be a place to post the slides as well. So we'll see where that goes. I know I have an updated set of slides from Bernard as well, and from maybe one of the other participants. So thank you again, and we'll talk to you tomorrow after the town hall meeting with the results. Okay.
Okay.
Is that it? Anything I missed, Ryan, Sean? Everything's okay? All right. Ryan and Sean and I are meeting in about half an hour.
So
So
I have a question. Where can we get the hard copy reports that they submitted?
they will be put on the NAR website. There's a section for NAR members only that is on R&D reports. I don't know if there will be a provision to make them available to people who aren't NAR members at this point, but
Well,
we can
speaking
discuss that with
selfishly, I'm a
Todd.
member, so I'm good.
Yeah, you're okay. I mean, there's a repository going back decades there
Yeah.
that we put together, and that is a good place to get ideas. And also one of the requirements is, has this been done before? And what did you do that's new or different? And it's a good resource to see what has been done in the past. So.
Yeah, so just excellent reports, guys. I enjoyed all 4 of them, so yeah.
Yeah, and thanks, Todd, for setting this all up, and Ed, and to the judges. It's a lot of work to read these. And
Yeah, you're very welcome.
reading them, it's one thing, understanding everything is not possible. But the talks really made a difference. I understood a lot more after hearing you speak. So thanks. All right, then we'll sign off, and we'll see you hopefully tomorrow or later today at the social hour. Okay, bye-bye.
Bye-bye.